chair you are sitting on right now. Feel the weight of your own body settling into it. Just, look at the screen illuminating your face, the walls of the room around you.
The steady rhythm of your own breath, right?
Exactly. You navigate your life with this deeply ingrained, unspoken assumption that the physical reality surrounding you is permanent. You assume that the atomic structure of your skin, the carbon in your bones, and the fundamental laws of physics governing this exact moment are an eternal, stable foundation.
But they are not.
No, they are absolutely not. The reality you are experiencing right now is an illusion of stability. Everything you can touch, see, and interact with is a temporary, unbelievably fragile phase.
It really is the ultimate cosmic illusion because, we've spent centuries building chemistry, biology, astrophysics, all on this underlying assumption that the universe is resting safely at the absolute bottom of its energy landscape.
Like we're on the ground floor of reality.
Right, the ground floor. But the mathematics of our most precise physical models are now revealing something that is profoundly unsettling. We are not on the ground floor at all. We are suspended on a precarious ledge, just resting in a state of highly fragile equilibrium. We exist in what theoretical physics calls a metastable false vacuum.
A false vacuum. The phrase itself sounds like something out of a cosmic horror story. But this isn't fiction. This is real. The fundamental quantum state of our universe is separated from total, absolute annihilation by this invisible, finite quantum energy barrier.
And today we are looking directly into that abyss.
Yeah, we are. We're going to examine the exact physical mechanisms that are essentially holding a gun to the head of the universe. We're looking at the subatomic triggers that could collapse this false vacuum, how the literal geometry of black holes might be acting as cosmic detonators, and the eerie reality that physicists are actively simulating this apocalyptic mechanism on optical tables in laboratories right now.
Which is terrifying in its own right.
Highly terrifying. And we are even going to look for the literal scars left in the sky by collisions with other universes that have already undergone this catastrophic transition. So to truly grasp the magnitude of this threat, we have to understand the fabric that holds our reality together.
Right. It all comes down to the Higgs field. And I want you to imagine this field not as a single particle, but as an invisible ocean that just permeates every single millimeter of the cosmos.
Okay, an invisible ocean.
Yeah. And in our current epoch, like right now, this ocean is not empty. It has a baseline pressure. It's a resting state called a non-zero vacuum expectation value.
I want to make sure I'm visualizing this correctly. When you say an invisible ocean with a baseline pressure, do you mean it's like the atmosphere? Even when the wind isn't blowing, there's still air pressure pushing against us.
That is actually a very helpful way to think about it. Even in the absolute deepest, emptiest void of intergalactic space, where there are no stars, no gas, no light.
Just total emptiness.
Exactly. The Higgs field is still there, and its pressure is fundamentally turned on. And that pressure sits at exactly 246 giga-electron volts.
246 JV. And that specific number is like the magic pressure that gives elementary particles their mass, right?
Yes. Without that exact value, electrons wouldn't bind to nuclei. Chemistry simply wouldn't exist.
You wouldn't exist. The universe would just be a chaotic storm of massless particles zipping around at the speed of light.
Right. So that resting state, this 246 GeV, dictates the exact geometry of our existence. In the mathematics of the Standard Model, we visualize this energy landscape as a Mexican hat potential.
Okay, so imagine the shape of a sombrero.
Precisely. Right at the very center, the peak of the hat, the field value is 0. But that peak is highly unstable. In the early moments of the Big Bang, the universe rolled down the slope of that hat and settled into the brim.
And that brim is the 246 GeV valley we live in now.
Right. And we assumed for decades that this valley was the lowest possible energy state, the true bottom of the universe.
But it's not the true bottom. It's just a local minimum. So think of our universe, everything we know and love, as a massive boulder resting in a small dimple on the side of a sheer, impossibly high cliff face.
I love that analogy. We are perfectly safe as long as the boulder sits in that dimple.
But the gun pointed at the universe has a trigger, and that trigger is a subatomic particle, the heaviest elementary particle in existence. We're talking about the top quark.
The top quark is an absolute anomaly in the Standard Model. It is incredibly massive. And because of its immense mass, it interacts with the Higgs field more violently than any other particle. It possesses a Yukawa coupling of order unity.
Okay, hold on. Yukawa coupling of order unity, that is some heavy jargon right there. A coupling is basically how strongly a particle interacts with a field, right? But what does order unity actually mean in practical terms?
Think of order unity as meaning the number 1. In quantum mechanics, interaction strengths are usually very small fractions. The electron, for instance, interacts with the Higgs field very weakly, so its coupling is a tiny, tiny decimal.
But the top quark's coupling strength is almost perfectly 1.0.
Exactly. It is inextricably aggressively bound to the Higgs field in a way no other particle is. So in the high-stakes mathematics of quantum field theory, this immense mass is not just weight, it is an active destabilizing force.
So if we take our current comfortable reality and start extrapolating it to incredibly high energy scales, energies that existed like fractions of a second after the Big Bang, far beyond anything we can generate in the Large Hadron Collider, a mathematical war reveals itself.
A very violent mathematical war.
Right. You have the positive forces of the gauge bosons, the W and Z particles, trying to keep the Higgs field stable, trying to keep the walls of our little valley intact. But then you have the top quark, and the top quark is fighting for the other side.
And the mechanism driving this war relies on something called radiative corrections. The vacuum of space is not empty. It is a boiling quantum foam of virtual particles continuously popping into and out of existence.
I always struggle with this idea of virtual particles. Are they real particles or just, mathematical ghosts?
They are temporary fluctuations in the underlying quantum fields. The Heisenberg uncertainty principle allows a pair of particles, say a top quark and an anti-top quark, to borrow energy from the vacuum, exist for an unimaginably brief fraction of a second, and then annihilate each other.
So they return the energy almost instantly.
Exactly. But even though they're fleeting, their temporary presence exerts a tangible physical influence on the fields around them.
It's like how a boiling pot of water shakes the stove even if no water spills over. The bubbling itself creates a physical effect.
That is a brilliant analogy, and those endless boiling loops of virtual top quarks utterly dominate the cosmic tug-of-war. Because the top quark's Yukawa coupling is so incredibly strong, these virtual loops pull immense amounts of energy out of the Higgs field.
So as you scale the ambient energy of the universe up, the top quark mathematically overwhelms the stabilizing forces of the W and Z bosons.
It does. It aggressively drives a vital parameter known as the Higgs-quartic self-coupling straight towards zero. And if you follow the equations up to an instability scale of approximately 10 to the 11th power g, something horrifying happens.
A coupling parameter turns negative.
It turns negative.
Meaning the wall of our comfortable little valley suddenly slopes downwards. It forms an energy barrier, just a thin wall. And on the other side of that wall, the landscape plunges into a vastly deeper, infinitely more destructive abyss, the true vacuum.
Right. The mathematics unequivocally indicate that our universe is inherently metastable. But the exact severity of this metastability, how thin that barrier is, how close we actually are to the edge, is currently the subject of an intense bleeding-edge tension in modern physics.
Because the top quark is the primary destabilizer, right? So measuring its exact mass is the single most critical task for determining the ultimate fate of reality.
Absolutely. But measuring a top quark isn't like putting a grain of sand on a digital scale. They decay almost instantly.
Like way before they even have a chance to form hadrons. So physicists have to sift through the quantum debris left behind to reverse engineer its mass. And right now, there are two distinct ways of doing this, and they don't perfectly agree, do they?
No, they don't, and that's where the tension lies. We attempt to extract the mass using a Monte Carlo method, which relies on simulating the complex cascade of particles that shoot out when a top quark decays.
Okay.
This statistical reconstruction gives us a stunningly precise measurement, accurate to about 500 mega-electron volts. But there is a massive shadow over this precision. The measurement is inherently reliant on simulating the behavior of the strong nuclear force, which is governed by quantum chromodynamics, or QCD.
Right, and QCD is notoriously messy. When you try to pull quarks apart to measure them, the strong force resists. The energy you pump in to pull them apart just snaps and creates more quarks out of thin air, resulting in a chaotic spray of particles?
Yes, hadronization. You've hit on the exact source of the theoretical opacity. In the fraction of a second before we can measure anything, the decay products of the top quark interact with everything else in the collision debris. We call this color reconnection.
Color reconnection. Okay, break that down for me.
Well, the strong force binds quarks using a property called color charge. As the particles fly apart, their color fields get tangled, break, and reconnect in wildly unpredictable ways.
So you are basically trying to measure the exact weight of a fragile glass vase by observing the trajectory of the shards after you hit it with a sledgehammer,
Exactly.
while all the shards are simultaneously melting and reforming into new shapes in midair.
That captures the absolute nightmare of the physics perfectly. And the stakes of getting this measurement right are cosmic. If the top quark mass is confirmed to sit at the higher end of the current experimental spectrum, around 173.3 GeV, the implications are staggering.
Staggering how? Like, what does that actually mean for us?
It means the instability of our vacuum is so severe that it dictates strict, retroactive rules on how the universe was allowed to form in the first place.
Wait, what do you mean by retroactive rules?
During the violent, high-energy era of cosmic inflation just after the Big Bang, the universe was saturated with energy far exceeding that 10 to the 11th GeV threshold. The quantum fluctuations were extreme.
Okay, so the universe was just boiling with energy.
Right, and if the top quark mass is that high, the math suggests those primordial fluctuations should have instantly kicked the universe over the edge into the true vacuum.
It should have ended before it even began.
Yes. To explain why we are here at all, physicists are forced to introduce massive, invisible constraints dictating a rigid mathematical relationship between gravity and the Higgs field during inflation.
Just to prevent the infant universe from instantly decaying.
Exactly. We only exist because of a deeply unnatural mathematical tightrope walk at the dawn of time.
So let's talk about the nightmare scenario. What actually happens if the barrier is breached? Let's go back to that boulder on the cliff analogy. We are safe as long as the boulder sits in that dimple.
For now, yes.
But the realm of the very small is governed by quantum mechanics, which means particles don't sit still. They jitter, they vibrate. And occasionally, a particle can tunnel through a solid barrier it shouldn't mathematically have the energy to cross.
Right, quantum tunneling.
So it's like a quantum earthquake hits our cliff. The boulder shakes, vibrates, and suddenly, probabilistically, it just phases straight through the rock wall and plummets down the cliff to the true bottom.
The formal physics term for the sun is a Euclidean bounce.
Wait, Euclidean bounce, that sounds like a math trick. What does it actually mean physically?
It is a mathematical trick, in a way, used to describe a profound physical reality. Normally, calculating the probability of a particle passing through a solid wall in real time is incredibly complex.
I can imagine.
But physicists found that if you translate the equations into imaginary time, a mathematical space governed by Euclidean geometry rather than standard space-time, the impossible act of tunneling through a wall looks mathematically identical to a ball simply bouncing off a wall.
Oh, wow.
Yeah. The Euclidean bounce is the mechanism that allows a microscopic region of space to spontaneously phase through the energy barrier.
And if that quantum tunneling occurs, it initiates an annihilation event unlike anything conceivable in classical physics. A microscopic bubble of true vacuum nucleates in the fabric of space.
And because the interior of this bubble represents a vastly lower, more stable energy state, it possesses an immense negative pressure gradient compared to the false vacuum outside.
I'm guessing that means it wants to expand.
It is practically compelled to expand by the deepest laws of thermodynamics. The wall of this nucleated bubble accelerates outward, feeding on the immense energy difference between the false and true vacuums.
And how fast does it grow?
Within an infinitesimal fraction of a second, the bubble wall is expanding asymptotically close to the speed of light.
And what happens when that light speed wall hits, say, the Earth?
Total instantaneous ontological erasure. Inside the bubble, the 246 GeV resting state of the Higgs field is gone. It has shifted to a profoundly different value.
So everything just vanishes.
Worse than vanishes. In the exact moment the wall passes through you, the fundamental constants of nature are instantaneously rewritten. The masses of electrons, protons, and quarks are fundamentally altered.
So atoms can't even hold themselves together anymore.
Without the specific masses we rely on, the delicate balance of electromagnetism and the strong nuclear force entirely fails. All atomic bonds instantly dissolve. Biology is obliterated. Planets, stars, and galaxies simply cease to exist as structured matter.
Okay, but let me push back here for a second. If the math says the top quark is dragging us toward this inevitably negative quartic coupling, and quantum tunneling means it's just a game of probability until a Euclidean bounce happens, why hasn't it?
That is the big question.
Right, because the universe has been sitting here vibrating on this ledge for 13.8 billion years. If the gun is loaded, why hasn't it fired yet?
That exact question moves us from the realm of spontaneous decay into something far more volatile. Because if we rely solely on spontaneous quantum tunneling, an unprompted Euclidean bounce in perfectly empty space, the math says the lifetime of our false vacuum should be infinitely longer than the current age of the universe.
Okay, so the probability of it happening purely by chance is astronomically low.
Right. But if you look at phase transitions in nature, they are almost never spontaneous.
Oh, wow. That makes perfect sense. Think about a bottle of incredibly pure, supercooled liquid water. You can chill it well below freezing, and it will remain liquid as long as it's perfectly still and perfectly pure.
Exactly. It takes forever for the water molecules to spontaneously arrange themselves into an ice crystal.
But the moment you introduce a catalyst, like an impurity, speck of dust, or a single grain of sand, you provide a nucleation site. The water molecules instantly grab onto that impurity, the barrier drops, and the entire bottle freezes solid in a heartbeat.
In the fabric of space-time, spontaneous transitions take forever. But what happens if the cosmos contains impurities? What happens if you drop a grain of sand into the supercooled liquid of the Higgs field?
I am almost afraid to ask. What is the cosmic grain of sand?
Theoretical physics has identified the ultimate cosmic impurity capable of seeding this phase transition, and it is a primordial black hole.
A black hole acting as a piece of dust in a bottle of supercooled water. That is a terrifying thought. How does a black hole act like a catalyst?
It is the integration of gravity into the quantum nightmare. We know that the presence of a black hole severely warps the geometry of spacetime around it. When physicists model the Euclidean bounce, that tunneling event, in a severely curved background, the geometry profoundly alters the mathematics.
How so?
The curved spacetime effectively eats the core of the quantum instanton.
I need to stop you there. Eats the core of a quantum instanton. What exactly is an instanton?
Think of an instanton not as a physical particle, but as a mathematical bridge through time. It is the specific trajectory a system takes as it tunnels from one state to another.
Okay, a mathematical bridge.
Right. And in empty, flat space, building that bridge takes an immense amount of energy. But a black hole bends space so severely that the distance between the here of the false vacuum and the there of the true vacuum is drastically shortened.
The gravitational well acts like a shortcut.
Exactly. It physically lowers the energy barrier required to transition.
So by warping the space, the black hole makes the wall of our valley thinner.
Drastically thinner. It profoundly lowers the action that normally suppresses the tunneling rate. But it actually gets worse.
How could it get worse?
We aren't just talking about the passive geometry of a black hole acting as a shortcut. We have to look at its active thermodynamics. Black holes are not entirely black. They emit Hawking radiation. And as a black hole radiates, it loses mass.
Wait, how does losing mass make a black hole a better catalyst? And usually things cool down as they evaporate. But with black holes, it's the opposite, right?
Yes. The mechanism of Hawking radiation is deeply tied to that quantum foam we discussed earlier. Remember the virtual particle pairs popping in and out of existence?
Right, the boiling pot.
When a pair forms right on the absolute edge of a black hole's event horizon, sometimes one particle falls in and the other escapes into space.
And the one that falls in carries negative energy.
In a manner of speaking, yes. To balance the cosmic ledger, the black hole must give up a tiny fraction of its mass to power the escape of the outgoing particle. Now here is the brutal irony. As the black hole loses mass, its event horizon shrinks.
Okay.
A smaller event horizon means the curvature of space right at the edge becomes much sharper, much more extreme. This sharper curve makes it easier to tear virtual particles apart, which accelerates the radiation process.
So as it shrinks, the radiation speeds up and it gets hotter and hotter.
A microscopic, evaporating primordial black hole generates an environment of incomprehensible extremity. In the final stages of its life, its temperature rises exponentially. The ambient plasma immediately surrounding the event horizon reaches unimaginably high temperatures.
So it's not just a passive shortcut anymore.
No, because the black hole is so incredibly compact, local thermal equilibrium is never truly achieved. You have this chaotic, microscopic hellscape where intense classical heat and violent quantum perturbations combine.
Creating a highly volatile zone.
Exactly, a volatile zone that physically assaults the thinned energy barrier holding the false vacuum intact.
It's not just a grain of sand dropped into the supercooled water. It's a hyperheated grain of sand actively vibrating the molecules around it, practically forcing the water to freeze.
The calculations are definitive. For certain ranges of the Higgs parameters, the rate of vacuum decay seeded by an evaporating black hole dramatically overtakes the rate of the evaporation itself.
Wait, really?
Yes. If a black hole reaches a specific, critical microscopic mass threshold before it finishes evaporating, the probability of it triggering the collapse of the Higgs vacuum approaches certainty.
Which introduces an incredible existential paradox. Because we know from these calculations that if a primordial black hole with a mass of less than 1 billion tons existed,
Which sounds huge, but in cosmic terms is a microscopic speck, about 10 to the 15th grams.
right, if a black hole that small existed anywhere in the universe, its evaporation would have already triggered a false vacuum decay.
The paradox is our own existence. The mere fact that you are sitting in your chair, breathing, and listening to this conversation is strict observational proof that these microscopic black holes must not exist in any significant numbers.
Because if they did, a true vacuum bubble would have nucleated billions of years ago and wiped the cosmos clean.
Exactly. It's a physical constraint dictated by our own survival. It tells cosmologists that whatever happened in the turbulent density fluctuations right after the Big Bang, it could not have produced a swarm of light, primordial black holes.
Because if it had, we wouldn't be here to run the math.
Our ongoing existence tightly constrains the parameters of physics beyond the standard model. But what if we don't just wait for the cosmos to provide an impurity? What if we attempt to study this catastrophic architecture directly?
Okay, if our existence proves these microscopic black holes didn't wipe us out, how can we possibly test this math? We obviously can't build a black hole.
No, we can't.
But this is where the story pivots from theoretical cosmic scale physics billions of light years away to the immediate, slightly paranoid reality of a laboratory here on Earth. Physicists are not just writing equations on chalkboards anymore. They are actively building this exact apocalyptic architecture on optical tables.
They're essentially simulating the end of the universe.
Right. And the breakthroughs in macroscopic quantum simulations over the past few years are just staggering. Researchers are utilizing what are known as programmable Rydberg atom arrays.
These aren't computer simulations running code, by the way. These are empirical, physical analogs of the quantum field theory, constructed atom by atom.
Let's break down how they actually do this. They use optical tweezers, which are literal microscopic beams of laser light. But how does light grab an atom? I mean, light doesn't have hands.
It relies on radiation pressure. Even though photons have no mass, they have momentum. By tightly focusing a laser beam through a microscopic lens, physicists create a steep gradient of light intensity.
Okay, so a bright spot and a dark spot.
Right. Neutral atoms are naturally drawn to the point of highest intensity, the focal point of the laser, because of the way the light's electric field polarizes the atom. The atom gets trapped in the beam like a marble resting at the bottom of a bowl.
Wow.
Using dozens of these bones, researchers grab individual neutral atoms and physically arrange them into highly specific one-dimensional rings or two-dimensional lattice structures. They are manually building a synthetic fabric of spacetime.
And once they have this lattice built, they bombard these trapped atoms with highly tuned 420 nanometer and 10,013 nanometer lasers. They force the atoms to undergo a two-photon transition, pushing the electrons out of their standard ground state and into a highly excited state, specifically the 70s Rydberg state.
Yes.
Why is 70s? Like, what does that actually do to the atom?
The 70 refers to the principal quantum number. In a standard ground state atom, the electrons orbit very close to the nucleus. But when you pump exactly the right frequencies of laser light into the atom, you kick an electron into an incredibly distant, weakly bound orbit.
How distant are we talking?
The 70th state inflates the electron's orbit to an immense size, up to 100,000 times larger than a normal atom. They essentially turn the atoms into macroscopic quantum balloons.
So by exaggerating their physical footprint to such an extreme degree, they induce immense, long-range van der Waals interactions between the neighboring atoms in the lattice.
Exactly. Even though the atoms aren't touching, their massively inflated electron clouds start to, feel each other. They become hypersensitive to one another. Their quantum states inextricably linked.
They have essentially created a synthetic quantum field.
Yes, and now comes the truly critical phase of the experiment. To mimic the false vacuum we live in, they use staggered detuning lasers. They intentionally introduce an imbalance into the system.
An imbalance.
They break the quantum symmetry, specifically the Z2 symmetry of the atomic spins, creating an artificial energy difference between the current state of the lattice and a lower energy state.
Whoa, slow down. They break the symmetry. What does that actually look like on the optical tip? Are they just hitting half the atoms with a different laser?
Not quite half. They apply a highly controlled, uniform microwave field across the entire array that slightly shifts the energy levels of the atomic spins. In a perfectly symmetric system, pointing up or pointing down would require the exact same amount of energy. But by detuning the lasers, they tilt the board. Suddenly, all the atoms pointing up represent a higher energy state, our false vacuum, and pointing down represents a profoundly lower energy state, the true vacuum.
And then they watch it collapse. Because the quantum array is a discrete system, they can literally observe coherent two-state oscillations. They sit in the lab and watch resonant bubble nucleation occur in real time.
It's incredible.
A localized pocket of the lower energy spin state spontaneously forms and begins to devour the surrounding lattice. They're literally watching a microscopic universe end.
And there is a fascinating constraint observed in these physical simulations. In the real universe, the true vacuum bubble expands at the speed of light. In the laboratory lattice, the bubble's expansion is bound by something called the Lieb-Robinson bound.
So it's like falling dominoes? The destruction can only travel as fast as one atom can physically interact with and knock over the spin state of the atom next to it.
That is a brilliant way to visualize it. The Lieb-Robinson bound acts as the absolute speed limit of causality within that specific discrete atomic system. It dictates the maximum velocity at which information or the phase transition can propagate.
It perfectly mirrors the relativistic speed of light constraint in a cosmic vacuum decay. It creates a localized temporal light cone right there on the optical table.
Precisely.
I have to push back here. Just speaking as a human being with a healthy sense of self-preservation, are we playing with fire?
I get that question a lot.
Well, is there a non-zero chance that by trapping these atoms, inflating them to 100,000 times their size, and actively forcing them to undergo resonant bubble nucleation, a physicist might accidentally trigger the real, actual collapse of the Higgs field? Could an optical table in Massachusetts accidentally delete the universe?
It is a profound visceral fear, but I can offer some comfort.
We must separate the map from the territory here.
These Rydberg arrays are a simulation of the mathematics governing phase transitions, utilizing the spin states of electrons. They are a physical analog. We are not manipulating the actual Higgs field itself, nor are we generating anywhere near the 10 to the 11th power GeV energy scales required to probe the real instability scale. The universe is safe from these specific lasers.
Okay, good. We're going to accidentally pop the bubble today.
Yeah.
But it's impossible to look at these experiments and not feel a chill, especially when you consider how hard science fiction has been treating these exact concepts for decades as cognitive laboratories for disaster.
Oh, definitely.
Writers like Greg Egan and Stephen Baxter have explored what happens when localized physics experiments go wrong. There's this brilliant, terrifying narrative concept where scientists try to create a localized bubble of novo vacuum inside a containment field.
A classic sci-fi trope.
Right, and according to their perfectly sound, Nobel-winning math, the new vacuum state is supposed to instantly collapse back on itself within a few picoseconds. It's supposed to be just a harmless flash of data.
But in the fiction, the predictive models fail. The experiment inadvertently triggers a macroscopic phase transition.
Exactly. Instead of collapsing, the newly nucleated vacuum stabilizes. The containment field shatters, and the novo vacuum begins to expand outward. Not at the speed of light, but steadily at exactly half the speed of light.
Expanding silently.
Swallowing the Earth, swallowing the solar system, and over centuries, completely rewriting the physics of thousands of star systems. It explores the ultimate horror, a localized anthropogenic apocalypse that fundamentally deletes reality piece by piece.
It's a chilling thought. But let's take that concept of expanding bubbles and scale it out from an optical table to the absolute limits of cosmology. Because if we know that a false vacuum can decay in theory, and we know that true vacuum bubbles can nucleate and expand,
we are drawn toward an ultimate mind-bending conclusion.
What if this has already happened? Endlessly. Over and over again. What if our entire observable universe is just one tiny outcome of a process that has been running for eternity?
You are describing the framework of eternal inflation.
I am. And to understand the mechanics behind this, we have to look back to the very fraction of a second after the Big Bang. In the early universe, space was dominated by the immense constant energy density of a false vacuum.
Okay.
And according to the mathematics of general relativity, specifically the de Sitter metric, a space dominated by a constant positive energy undergoes exponential, violent expansion.
So the space itself is stretching faster than anything moving within it.
Much faster. And within this rapidly inflating, hyper-expanding background, violent quantum fluctuations are constantly occurring. Occasionally, those fluctuations cause local regions of the space to tunnel through the potential barrier, just like the Euclidean bounce we discussed earlier.
So a true vacuum bubble nucleates.
Right. Inside that specific bubble, the massive inflation stops, energy is released into matter and radiation, and a universe is born just like ours.
But the horrifying fractal beauty of it is that the overarching false vacuum outside the bubble is expanding exponentially faster than the newly nucleated bubble can grow. The bubble wall is expanding at the speed of light, but the empty space between the bubbles is stretching faster than light.
Which ensures the false vacuum is never, ever entirely depleted. It is a runaway, perpetual process. The exponentially expanding space continuously generates new bubbles, indefinitely into the future.
It births a multiverse.
Exactly. An infinite fractal-like structure of distinct, isolated universe bubbles, forever separated by an infinitely expanding ocean of high-energy false vacuum.
And our entire observable universe, every galaxy, every quasar, every speck of dust we have ever mapped with our greatest telescopes, is entirely contained inside just one of these countless bubbles.
But here's the cosmic detective story. If we are in a bubble and there are infinite other bubbles being generated around us in the primordial past, is it possible that our bubble bumped into another one before the space between us stretched too far?
Cosmic bubble collisions. Now, some physicists roll their eyes at the multiverse, calling it unfalsifiable metaphysics, because we can't build a telescope that looks outside our universe.
But the physics of bubble collisions gives us a loophole. It gives us a rigorously testable observational framework.
Because if another universe collided with ours in the deep past, the immense energy of that collision wall would have sent shock waves through the initial conditions of our local spacetime.
Those perturbations would not simply fade away into nothing. They would be permanently, irrevocably inscribed on the oldest light in the universe. The cosmic microwave background radiation, or CMB, which is the afterglow of the Big Bang itself.
Think of the cosmic microwave background, like the foam on top of a freshly poured cappuccino. It's a physical snapshot of the universe's temperature from when it first cooled down enough to let light travel freely.
That's a great visual.
What cosmologists are doing is using advanced mathematics to scrutinize that foam, looking for the exact symmetrical crease left behind by two distinct bubbles smashing together right before the foam froze in place.
Theoretical models and full general relativistic simulations of these de Sitter space collisions predict highly specific observational signatures in the CMB. We wouldn't just see random noise or standard hotspots.
What will we see?
A collision would induce a very localized temperature modulation, typically taking the form of a sharp, circular disk in the sky.
And the geometry of two intersecting spheres dictates a very specific pattern within that disk.
Crucially, these signatures would exhibit strict azimuthal symmetry.
What does azimuthal symmetry actually mean when we look at the sky? Like if I'm looking at a map of the CMB.
It means that if you draw an axis right through the center of the collision scar on the sky map, the temperature patterns would be mirrored identically on both sides of that axis, radiating outward in concentric rings.
Well,
furthermore, advanced simulations show that these collisions would not just alter the temperature, but would profoundly influence the polarization transfer functions of the CMB light.
and we are actively hunting for these scars right now. Cosmologists have built an entire observational pipeline using high-resolution, full-sky data from the Planck satellite to search for these exact collision signatures.
But this is an incredibly complex data extraction problem. You have to avoid the cognitive bias of pareidolia.
The human brain's tendency to see faces in clouds or to falsely identify patterns in random cosmic noise.
Right. To eliminate this, the research teams rely on rigorous modular Bayesian algorithms. And at the heart of those algorithms is a mathematical tool called a needlet transform. Needlets are spherical wavelets that act like incredibly sophisticated edge detection filters.
They're described as being highly localized in both real space and harmonic space. That sounds smart, but what does it actually mean? How do they detect edges?
To understand a needlet, imagine trying to find a perfectly straight artificial line drawn in the sand of a massive undulating desert.
Okay, a line in the sand.
If you just look at the overall height of the dunes, which is harmonic space, you miss the line. If you just look at a few grains of sand real space, you also miss the line.
So what does the needlet do?
A needlet is a mathematical wave packet that lives on the surface of a sphere like our map of the sky. It is designed to ignore smooth, gradual changes like the natural cosmic variance or the massive, glowing dust clouds of our own Milky Way galaxy.
It filters all the normal stuff out.
Exactly. Instead, it only lights up when it encounters a sharp, sudden gradient change. The algorithm sweeps the needlets across the CMB data, mathematically filtering out the foreground noise, specifically searching for the sharp, bruised physical edges of a collision between our reality and another.
That is just incredible.
Yeah.
But before we wrap up, we need to touch on one more concept. Because if we're going full sci-fi physics with expanding bubbles and multiverse collisions, we have to talk about strange matter.
Strangelets. That is a truly horrifying hypothesis.
It really is. It shifts the threat away from the vacuum itself and onto the actual matter we are made of. So inside protons and neutrons, we have up and down quarks. But there's another type of quark, the strange quark.
Right. And under extreme pressure, like inside the core of a neutron star, up, down, and strange quarks can combine to form what we call strange matter. The terrifying part is the strange matter hypothesis, which suggests that this state of matter might actually be more perfectly stable than regular matter.
Meaning it's the true ground state of matter.
Does that sound familiar?
Very familiar. And if it is the true ground state, a single microscopic droplet of this stuff, a strangelet floating through space and hitting the Earth, could trigger an unstoppable chain reaction.
It would just touch a normal atom, realize it's more stable, and convert that atom into strange matter, which then touches the next atom. And the next.
Exactly. It would just endlessly convert ordinary matter into strange matter, converting the entire Earth into a hyperdense glowing sphere of strange quarks in a matter of hours. So whether it's a true vacuum bubble or a microscopic strangelet, the overarching realization is unavoidable. When you step back and look at the entire board, from the top quark pulling at the absolute threads of the Higgs field, to microscopic black holes acting as hyperheated cosmic triggers, to the strange matter hypothesis, the architecture of space-time is incredibly, fundamentally fragile.
It really is. We navigate our daily lives with a profound evolutionary bias towards stability. We assume the ground beneath our feet is solid because it has always been solid in our historical experience.
But history isn't physics.
Exactly. The mathematics of our reality reveal that we are balancing on a precarious quantum edge. We are a temporary arrangement of energy resting in a dimple on the side of a cliff, completely blind to the depths below.
And that brings us to the final chilling thought I want to leave you with today. Let's assume, somewhere out there in the vastness of the cosmos, billions of light years away from Earth, a dying primordial black hole finally evaporated.
It reached that critical temperature, the quantum instanton warped under the severe gravity, and the Euclidean bounce occurred.
The false vacuum collapsed. A tiny bubble of true vacuum nucleated. Because the wall of that bubble is driven by an immense energy gradient, it accelerates instantly, expanding asymptotically close to the speed of light.
And because it moves at the speed of light, it gives absolutely no warning. Light is the absolute fastest way any information can travel through the universe.
Which means the visual evidence of the collapse, the light from the dying stars, the radiation from the shattered galaxies, the distortion of gravity itself travels at the exact same speed as the destruction.
They arrive at the exact same moment.
If that bubble nucleated billions of years ago, a light-speed wall of new physics, a wave of absolute ontological annihilation, could be rushing toward Earth right now. It could be 10 light years away. It could be the distance of the moon.
There is mathematically no way to know.
And if it hits us, the total annihilation of our reality would arrive before the light carrying its image ever reached our retinas. The sky wouldn't change. No alarms would sound. We would simply cease to be, deleted between one heartbeat and the next, without ever having the sensory capacity to see it coming.